Hi, Mitch Wenger back with another video on data analytics and machine learning. In this video, we'll discuss the use of nearest neighbors in predictive modeling. Hope you enjoy. Okay, let's get started. How can we use distance and similarity in predictive modeling? And remember, predictive modeling is supervised learning. Say we're given an example whose target value we want to predict. Well, we can scan through all the examples we have out there and choose several that are the most similar to our new example. And of course, the key is that in those several we select, we already know what the target variable is. At that point, we now can predict the new example's target value based on these nearest neighbors' already known target values. And we can do that using classification to look for those nearest neighbors and derive a target class for our new example. We could also do that using a regression approach, in which case we derive the target value using the means or the medians of those neighbors. Remember, in data mining, we place examples, feature vectors that is, somewhere in our data space. Now, if we have a new case we want to consider, like we just mentioned, we can calculate the distance between this new case and other cases, again, where we already know their target variable. And that's the idea behind what we call k-nearest neighbors. Coffee, wine, beer, and liquor aficionados can have a field day with an approach like this. If you think about all the characteristics people use to describe these beverages, aroma, nose, finish, chocolatey, earthy, hoppy, fruity, peaty, dry, smooth, bright. If you have a scale for each of those attributes, you can find new variations of your favorite beverage that are similar to those you like out of the dozens, hundreds, or thousands of options you may have available. In music, Pandora originated the Music Genome Project, and they used an approach similar to this to classify music based on a variety of attributes. And of course, when you listen to something and you give it that thumbs up, well, then they look for other music with similar attributes that they predict you might like as well. Newer services such as Spotify, Amazon Music, and the like have also incorporated this approach as well. At its most basic, k-nearest neighbors uses a majority rules approach. For a new feature vector or case, we look at the k-nearest cases in the data space to determine the value of the new case. Whatever the majority are, that's what we predict the new case to be. Beyond that, there's a lot to consider. How many neighbors should we evaluate? 1, 3, 500? This is an issue to consider and should become part of the testing you go through when you create a new model. And we'll talk more about that later. Getting back to our example, here, let's see, we want to decide whether our new example will accept our offer. And we choose to evaluate the nearest 5 examples. And we can see from this table that 3 are N, while 2 are Y. So this would result in us predicting that our new prospect will not accept our offer. So we may not send it to them. Now you might ask the question, why don't we just look at the nearest neighbor? That is the one nearest neighbor. Why not set K to 1? Well, we build these models with training data. And these are examples we've collected where we already know the classification category. And you can think of the examples that you've read about or heard about earlier, like Capital One, for example, building all that training data. Now let's take a look at these two charts. If you look at the model on the left, we're using one nearest neighbor to predict. And as you can see, we end up with many disjointed decision boundaries in a very specific model. As a matter of fact, we call this overfitting, and we'll talk about it more in future lectures. Now on the right, the model uses 30 nearest neighbors. So we've set K to 30. And here we end up with pretty clean decision boundaries and fairly well-defined decision spaces. All right, so you might ask, well, why not just evaluate all the neighbors? Make it 500 or n, whatever your n happens to be. Well, in this case, that would result in a single classification space that's simply the category with the most cases, basically a majority. So we would always predict the majority class. All new values, any new unknown value, we just predict to be that majority class. And that's what we call a baseline predictor. And that's a starting point for determining how good a model might be, actually. The problem is we would predict all those values to be that majority value no matter where they ended up appearing on the chart. Same thing if we did a regression using all the neighbors, we would predict the average of all parameter values. So determining how many neighbors is part of the evaluation. One general rule of thumb in practice, we do set K to an odd number so that we minimize the possibility of a tie. So for K nearest neighbors, K is what we call a complexity parameter. The value of K determines how simple, over on the right, a simpler model, or complex, over on the left, a very complex model, our model will be. More complex models have a greater tendency to overfit specifically to the training data, which reduces their generalizability to the wider population of all these unknown data points we will encounter in the future. So the next question we want to consider is distance. Does distance matter? In other words, should closer neighbors be more influential? This is definitely another consideration you should put into your model building. How much more important should closer neighbors be? What type of weighting can you give them? Again, your decisions will affect the performance of the model. So in our previous example, we evaluated the nearest 5 examples, just looking for a majority, and we ended up predicting, no, our new prospect is not going to accept our offer. On the other hand, if we do let distance matter, we've already calculated those distances, so we can assign weightings based on those distances to how near our comparison points are to the new example. And from there, we can determine how much they will contribute to the prediction calculation. Here, we can see that the first 3 examples each end up contributing more than 30% to the prediction, while the last 2 contribute less than 1 each. We basically took the distance weighting and turned it into a percentage such that all the percentages added up to 1. So in this case, we end up predicting why. Yes, they will accept our offer. So we'll talk again a little bit more about that later. So this weighting concept also works for lots of other prediction approaches. You've probably used it in regression already. And probability estimation, it works there too. So it brings a scoring approach to the process, which reduces the importance of determining how many neighbors we need to select. Now, there are some considerations that we need to discuss regarding k-nearest neighbors as well. The first one is intelligibility. Now, in fields such as medicine and law, case-based reasoning, which is similar to k-nearest neighbors, it's used all the time. So we certainly have some parallels with the legal profession, so k-nearest neighbors might make sense in certain situations. Another aspect of intelligibility is that decisions are relatively easy to explain using k-nearest neighbors based on the contributions of those neighbors. Most people understand this approach intuitively, although how you phrase and present these representative neighbors should be a part of your strategy. So, for example, the movie Captain Marvel was recommended to you based on your interest in the Avengers, Spider-Man, and Wonder Woman. All right? Now, in some situations, k-nearest neighbor may not be such a good idea. So, for example, you're a lot like these deadbeats, the Smiths and the Jones, who defaulted on their loans. In that case, you might want to think of a different way of phrasing that. As a matter of fact, there may even be some legal restrictions on which types of models can be used for various things, calculating credit scores, for example. The next consideration is dimensionality, and we're going to talk about that more in just a minute. So I'm going to skip that for now and move right to computational efficiency. So computational efficiency is another thing you do want to consider in your models, depending on how quickly you need to be able to build or refresh your model, and or how quickly you need to make the decision that the model will be used for. Now, k-nearest neighbor is great for model building. It's called a lazy learner because there's really little, if any, computation effort when building the model. You just throw any new data points you know the target value for into the model, and there you have it. The only real learning done during model building is to determine what your value of k is going to be. On the other hand, k-nearest neighbor is not very efficient at decision time, because anytime you get a new data point, you have to go out and query the data space to find out what all these nearest values are in order to make your prediction, and that becomes expensive. And in this case, when we say expensive from a computing standpoint, that means we're using more computing resources on the server. It's generally going to take longer, and that means something else can't be done. Now, when we add distance to the k-nearest neighbor calculation, that increases the computational expense even more. So k-nearest neighbor isn't necessarily a preferred technique for applications that require extremely fast decision making. Now, tools have been making quite a bit of headway in speeding up this decision-making process, but still, it's something you want to keep an eye on when you consider k-nearest neighbors. Now, let's get back to dimensionality. When we're using nearest neighbors, we generally consider all the numeric features. That means we can have a scaling problem because different features are often going to use widely different value ranges. So that causes a computational problem in that different features will naturally be weighted more just based on the range of their scale. We can address that problem by standardizing and normalizing those values. But more importantly, having too many attributes or irrelevant attributes may confuse those distant calculations. And therefore, we end up with what we call the curse of dimensionality. That is, we have high dimensional data spaces. Now remember, k-nearest neighbor is not that efficient at decision time. So if we have to consider more dimensions, again, that makes things more expensive. Also, if we have too many dimensions that aren't really all that important to the real decision of interest, we still end up using them in the calculation for k-nearest neighbors, possibly confusing the prediction that results from that calculation. So we've got a couple ways that we can approach this dimensionality problem. Solution one would be what we call feature selection. And this can be done in a number of ways. We can do it manually by using the knowledge we have of attribute relevance in previous decision processes we've been involved in. And this is one of the main ways that the data mining team can inject what we call domain knowledge into the project, into the model. So it plays a big role here. We can also use automated feature selection tools that are built into a lot of data mining software products these days. And we'll discuss some of these in a future video. Solution two is that we can tune the distance calculation we use in the model. We can manually adjust the weighting of different attributes or even eliminate those that aren't important to you in the decision process. Well, I might not care how hoppy my beer is, so I'd take that out of my calculation model. So as you might imagine, domain and specific business problem knowledge play an important role here as well. So that's a brief introduction to k-nearest neighbors. I hope you found this video useful. Be sure to check out the other videos in this series.